Started. Thanks for coming. Happy to introduce David Harwath. He's a professor in the computer science department, and most everyone in AI and machine learning now works with images or language or text. And David, I think, is one of the few people who works on speech, AI for speech. But I think it's a super interesting modality that more people should learn about and work on. And so I'm excited to hear about what you're doing in the area.
Okay. All right. Thank you so much, Adam, for the introduction, for hosting me at the seminar series. I'm going to be talking today about both speech generation and sound, just general audio understanding in the era of large language models. So I don't need to really introduce LLMs, to anybody. I think they're so ubiquitous now in NLP and beyond. And we've gotten to the point where most of the standard tasks that people used to work on and develop specialized models for have just been cast as an autoregressive sequence continuation problem, given some kind of prefix or some kind of prompt, where you give the model an instruction, like reverse the order of these following words, and you tell it hello world, and then it outputs world hello. And just about all of these models are based upon transformer decoder architectures that require the input sequence to be tokenized into some set of discrete symbols, which is very, very easy to do with text because we have things like byte pair encoding, or in the worst case, you can fall back to using characters or words. But we've seen over the past several years, there's this trend of making LLMs more and more multimodal, so bringing them away from just processing text and allowing them to process images, video, even audio signals. And what's really cool about this is that it multiplies the number of tasks that the model can perform. It can start doing reasoning, over not just textual inputs, but for example, this demo video shows how you can upload a image of your living room to Llama. This is a Llama 3.2 demo, and it captions the image that it sees, and you can start asking it things like suggesting, what kind of decorating upgrades and things like that should I be doing to my room. So it can reason across multiple modalities. And so the knowledge and abilities that the model seems to have learned from processing text then are portable to other modalities. So speech and audio have been no exception when it comes to that community trying to get on board the LLM bandwagon and integrate audio and speech as inputs and outputs to these models. The general approach, it kind of follows two patterns. You're either building a LLM which can take as input speech and text or audio and text, but then it would only generate text as an output. But then there's also other models which actually try to add the generation ability of like generating speech as an output so that you could engage, say, in like full duplex dialogue, spoken dialogue with these kinds of models. So the work that I'm going to be presenting today is all work from my lab here at UT Austin, which focuses on trying to expand the range of abilities that these kinds of joint audio and text language models are capable of doing. So the general themes are we're going to be looking at how can we modify these models, either like in the way that we build them or in their training objective to add new capabilities, or what kind of new data sets can we collect to support training on new tasks for audio and text. So I'm going to start by talking about several lines of work in my lab on speech generation and editing. So that'll be the first half. And then the second half, I'm going to be talking about reasoning, training LLMs to reason on spatial audio. So not just understanding what they hear in terms of the speech that somebody's speaking or that a dog is barking, but to actually understand the spatial relationships between different sounds if you give them, say, multi-microphone input that can encode that spatial information. And if time permits, which it probably won't, but just in case, I also have a little bit of material prepared on even more multimodal audio processing, where we jointly process video, audio, and text together for dubbing tasks. Okay, so I'm going to start by talking about the VoiceCraft model, which was developed by Puyan Peng, which he was a PhD student with me at UT. He just graduated. He's now at Meta working on the superintelligence team. But this work was sort of towards the end of his PhD and published last year at ACL. So I want to first talk about what the speech editing problem is. The task is that you've got some kind of waveform. Imagine you're a content creator, or you're recording an audiobook, and you record a long line, and maybe you flub or mispronounce a couple words in the middle, and you want to go back and edit it and fix those mispronunciation errors, say, but without having to re-record everything all over again. So the idea is that you want to replace some words within the waveform, but you want to maintain all of the original characteristics of the audio. So you want to keep the speaker's identity, whatever kind of emotion or prosody that they were speaking with, whatever kind of background noise was present, like if there's music in the background, all of those things should not be edited. We should only be editing the content. The generated speech also has to naturally flow into the context has to flow into the generated speech, and then the generated speech has to flow back into the surrounding context, right? Otherwise, it would sound very, very unnatural and discontinuous. So to concretize that a little bit, I'm going to play an example. I'll first play an input waveform to the model that I'll be presenting today.
It was a glance of inquiry, ending in a look of chagrin, with some muttered phrases that rendered it more emphatic.
So say I wanted to change the words glance of inquiry ending in a look of chagrin to a look of disgust followed by a curled lip. I would give the model the original waveform, I would give it my edited text, and then out would come the edited speech waveform.
It was a look of disgust followed by a curled lip, with some muttered phrases that rendered it more emphatic.
Okay, so that's the setting. And now I'm going to be talking about how we actually built this thing. But before I go into that, I also just want to briefly mention a very closely related problem that people work on in my field, which is voice cloning text-to-speech synthesis. The idea here is that given some kind of enrollment utterance, which is short, maybe 3 to 5 seconds, you would give it to the model, and it would learn to mimic that person's voice based upon that enrollment utterance, but you could generate entirely new text strings. We're going to be building a unified model that can handle both of these tasks, because we're just going to view this as a special case of editing where we're doing an insertion edit at the end of an existing report.
Is stylization a different problem? Like if I want to change the accent?
Yeah, so that would be more like voice conversion.
So that you will not be talking about that.
Yeah, we will not be. I mean, you could imagine.
Is it doable or?
It is doable. I mean, even this model can kind of do that. I could take a speech recognizer and recognize the words that you're speaking, but then take my voice and give that to a prompt to the system, and it would resynthesize what you said in my voice.
I see.
That's a little bit different from what people usually think of in terms of voice conversion, which is more kind of like you imagine the voice masking technology that they use in courtrooms, where there's it preserves the exact time alignment and maybe the prosody between what you generate and what the input is. Whereas this model would just keep the content the same, but it may give you a different speaking rate, things like that. So yeah, so that's an entirely different problem. I'll just play a quick example of this. So here's the reference recording. Here's Dave Chappelle.
Like there's this one sketch we did that was about
and then we can synthesize new speech in Dave Chappelle's voice.
I don't want to make it as a thing where I'm absolving myself of any responsibility.
Okay, so obviously there's an enormous number of commercial use cases for this kind of technology, from video games, customized on-demand advertising, have an audiobook read by your favorite voice actor instantly. Deepfakes. I have some slides on that later on, which I can offer my perspective on what we should be doing to defend against that. Highly personalized digital assistants, also speech prosthetics for people who may have lost their voice already, and also voice cloning speech-to-speech translation, which has enormous commercial applications in movie dubbing from one language to another. Okay, so now I want to talk about the models that we're actually going to be training here. So this work is it was based on and really was inspired by Microsoft's Volley model, which came out in I think 2023, which was the first model that really popularized this idea of training a language model jointly on speech and text for the TTS problem, specifically the voice cloning TTS problem. So they demonstrated that these kinds of models could actually handle that task. They didn't release any model or code, only demos. So the contributions really in our work were that we developed, we trained and released as open source the very first large-scale open neural codec language model, which got 8.4 thousand stars within just a couple weeks of being released. I think it was #1 on GitHub for a couple days at least. We also set a new state of the art for TTS quality. We actually beat the Volley model in terms of the quality. And we also extended the capabilities of Volley beyond TTS, and we enabled it to do that speech editing problem that I talked about. So I want to talk a little bit about the technical details that go into building an LM over speech, because it's quite different than building a text-based LM. We don't have just 1 or 2 tokens per word in a speech LM. Our waveforms look like this. Nominally, they're sampled at least 16,000 samples every second, and that's already a relatively low quality. CD quality would be more like 40,000 or 44,000. Yes.
Your previous slides, what was the state of the art before like transformer-based LLMs in the speech editing? Like, was this even possible?
So there weren't really that many models that looked at speech editing. Most people working in this area were doing like voice cloning TTS. Even then, the models didn't really look like, they didn't look like LLMs where you tokenize the reference audio and do sequence continuation. So there's another subproblem in the field, which is like speaker verification and speaker identification. So it's basically, tell whether these 2 waveforms were from the same person or recognize who's speaking. So the state-of-the-art technology for the last 10 years in that area has been to build these like speaker embedding models. You can think of it as like almost like an image classifier where you can extract an embedding for an input image. We can do that for an arbitrarily long waveform, and it captures some information about who the person is. So people would be building models that were based on LSTMs that are generating spectrograms that you can then apply a vocoder to map it back to a waveform that were conditioned on something like a speaker embedding. So that's sort of what the state of the art for this looked like before people moved to the LLMs. But the LLMs they're a lot more powerful, just in a general ability to generate really naturalistic sounding speech. Yeah.
So if you can do voice cloning for speech editing, can you just do like speech to text, edit in text, and then generate text with the voice clone? Will you get that? Why do you need one model?
You can, but the thing is that, I think you sort of get into like the desires of content creators. They may not want to just have everything be synthesized. They might want to have the majority of the speech be what they actually recorded, and just be kind of like ad-libbing a few missing slots. So I think it gets a little bit into the preference of like how people actually want to use these systems. So when it comes to actually tokenizing speech, this is a really hard problem that, basically half of the model and half of the training time is spent on solving this. So as I mentioned, we've got 16,000 samples a second. So if you're going to represent every single sample as a token, you very quickly reach an intractably large number of inputs for a transformer to handle. So we're going to have to do some kind of downsampling and compression. So the main technique that people have been using for this is based upon vector quantizing autoencoders. So everybody is familiar with a standard autoencoder. You map the speech to some kind of continuous latent space with your encoder, and then your decoder maps that back to a waveform. There's standard techniques for this based on doing transposed convolutions, on the waveform samples and things like that. We can make it very efficient. But the problem is that if you want to actually do language modeling within this latent space, it's difficult to do that with continuous vectors. So we need some way of quantizing it. So in 2017, Aaron Vandenoord proposed a vector quantizing autoencoder, which basically takes those continuous latents, quantizes them with some kind of learnable codebook, and then those discretized latents are used to do the reconstruction. And so, of course, when you do this quantization, you're going to incur some kind of quantization error between your continuous input and then whatever the codebook vector that you snapped it to and the output was. So the advantages of doing this kind of quantization is that, now we have a discrete finite size vocabulary that we can actually control with a relatively low frame rate. And so it's possible to start thinking about training language models over these discretized latents. And we also have our decoder for free. So we don't have to train a separate vocoder to learn how to reconstruct waveforms given these latents. It just comes for free as part of training the autoencoder. But the problem is that large quantization error, when we do that quantization, is going to lead to poor reconstruction quality. Yes.
What is the size of this discretization usually? And how many tokens would that?
Like how many tokens would come out of here? So somewhere around 50 per second. So it's still way higher density.
How many possible tokens are there?
Oh, like in the vocabulary size, on the order of several thousand. I can mention, it's actually more than that, but I'll mention it on the next slide. So the solution to, solving the artifacts that arise when you try to resynthesize these tokens that have a lot of quantization error, the general solution that the community has identified is that we basically do residual quantization. So you have one stage of quantization, which is what I just showed, but then you take the error term and you just quantize that. And then you take the error term of the second quantization and you quantize that. And you do this however many times it takes until you reach a acceptably low quantization error. So what this results in is not just a single stream of discrete tokens, but now we have a stack of tokens. So our speech is going to look quite different from text because we're not going to have one stream of tokens. We're going to have this parallel stack. This stack is usually somewhere between like 8 and 16 tall. So 8 to 16 VQ layers. And each one of these quantizers might have a vocabulary size of 2048. So you could have 2048 times 8 to 16 is the total number of tokens here. But again, you're going to have this sort of, combinatoric, even larger like implicit number of representations. Okay, so now that we've talked about how to actually quantize speech and tokenize it, I want to talk about the editing problem. And so we're going to cast this as an in-painting problem where I've got some kind of span of the waveform, which is aligned to the words that I want to replace, and I want to put down some new words there, and then generate that waveform that would reflect those new words. So it's quite different in the challenges from regular TTS, because here we have to really pay attention to avoiding artifacts and discontinuities at the boundaries. And we also have to make sure that the prosody remains consistent throughout the utterance after we in-paint it. So things like the pitch contour, right, need to actually fit and flow into and out of the generated segment. So naive autoregressive, like left to right prediction, when you do that, it's only possible to condition on the past context and not the future. So, a naive model would not be able to look to see what speech is coming next in order to predict, well, how should the person's pitch, move such that it stays continuous when you move out of the edited segment. So the solution that we're going to use to that is a trick where we essentially say, okay, if you want to mask this middle span and infill that, but you don't want to touch the beginning or the end here, we're going to take all the tokens that corresponds to the region that you want to in-paint, and we're going to move them to the end of the utterance. So you'll have prefix, blank, suffix, it's the end of the utterance, and now I'm going to echo back that blank token. And this should basically cue the model to go ahead and generate the infilled segment here. So if you do this rearrangement, then the model can actually look at the left context and the right context before it has to go back and refill the missing context.
So could you say that again? Sorry.
Yeah. So essentially the idea is that if I want to in-paint this middle section of the utterance, and I want to do it in such a way where I can condition on both the past and the future, but I want to do it with an autoregressive model, I'm going to need to do some kind of rearrangement of the tokens.
Right.
So what we do is we take that span that you want to mask, which is in the middle of the utterance, we move it to the end and we replace it with essentially a special token that represents blank. There is something missing here.
Okay.
So it's the model, if you're thinking left to right, it reads the prefix, there's something missing, it reads the suffix, we cue it to say this is the end of the utterance, and we just echo that same token.
Why don't you do a verb type training?
Yeah, okay, why do you need autoregressive?
So one of the reasons is because you don't actually know how long the generation should be. What I mean by that is if you want to replace picked with versus plucked, then you don't know how long, like how many tokens I should actually in-paint.
But so one thing you can do is you could have a max length, and then if it just ends, it generates an end, and then you just remove everything else after.
I guess you could do that.
Awesome.
Yeah. Yeah, I mean, I think, yeah, it would, it's a different way.
So maybe ask the question different way. Are you using any pre-trained autoregressive model already and putting this stuff into it?
No. So we're training this
It's trained from scratch, right?
Yeah.
So then you have control over the other.
We do. I think that, you know, you're right. So basically you're saying, okay, you could define some maximum total like duration that you would want to in-paint
Maybe,
and then say, okay, my training examples should essentially tell the model that everything after this point is padding and you can generate, you know, the anything before the padding is what you would want to keep and you chop off the rest. I mean, you could do that. I think that it would make training more expensive because as I'm going to show, we can actually do very, very long edits. In the subsequent follow-up work that we have here, we actually generate up to a minute of speech. And so,
no, but the problem is if you have very long speech and you want to change something, but there's a lot of other stuff that doesn't need to be changed, you might lose context. If you do it your way.
what do you mean you might lose context if you?
So you put Peter Piper and then
Yeah.
instead of a peck off, suppose it was like 7 paragraphs.
Yeah.
And then the end of it, but now we say, okay, I want to change something in the beginning. Then with your method, you would have to like go all the way back to the beginning.
In terms of like, it would be a very, very long sequence.
It'd be a very long sequence and you might lose context.
Uh,
But anyway, yeah,
Yeah.
I don't want to like brainstorm your.
yeah, no. It's a good point. I mean, you could do BERT style training here. I think it's an alternative that I think you could probably get to work, but this also works. So this is the strategy that we're going to be using instead of that, this sequence rearrangement technique. We're also going to run into this problem of predicting parallel tokens, right? So we don't have just one single softmax prediction head, but we actually have a number of softmax prediction heads equal to the number of quantizing codebooks that we use. And it turns out that it's a problem to try and predict these all in parallel because there's actually some dependence between these because the second token stack or second layer within this token stack is the residual, it's the error term of the first one. So you would actually want to have some kind of model, which, you know, you could either run like an RNN in the vertical direction, or, you know, you need to give the model some kind of way to condition on what like the first VQ output was before it predicts the second one. So the technique that we're going to use to do that, rather than having like an auxiliary model, is we're just going to insert this diagonal slant in the tokens. So what we're going to do is we're going to predict we're always going to have a time delay of 1 between each subsequent codebook prediction step. So when I'm predicting, you know, I'll predict the first codebook layer for time step 4 at the same time that I'm predicting the second codebook layer for time step 3, and then I'm predicting the third codebook entry for time step 2. Right. So in this way, the model actually always has information about the lower codebook entries before it's predicting the higher codebook entries for a particular step. So if we put it all together, we end up with a relatively complex pipeline where we take our audio input, we tokenize it with our neural codec model, we do the sequence rearrangement based upon where we want to edit, and then we apply this delay patterning technique. But after all of this is said and done, now we've got something where we can actually just autoregressively train a left to right encoder only model over these kinds of token sequences. Okay, so the model then would look something like this. Like I mentioned, we're just going to be using a pretty vanilla transformer decoder. Over those rearranged sequences, we're going to give phonymized transcriptions of the targets in order for the model to be able to know what speech should actually synthesize. And so then the objective is just given a standard language modeling objective where we maximize the probability of the token sequence conditioned on the previous tokens as well as the phonymized transcript. Okay, just a few training details in case anybody is interested. I mentioned we're doing large scale training here. What does that actually mean? 10,000 hours of speech is what we're training on over 3 broad domains. So we're using YouTube videos, audiobooks, and podcasts. So that covers sort of the range from, you know, a single speaker speaking very, very in a very clean environment with a high quality microphone, reading very formal speech, to conversations between multiple people that are spontaneous and maybe have a lot of background noise, say in the YouTube domain. And we actually found it advantageous to not use an off-the-shelf codec model, we actually had to retrain our own to get good reconstruction quality across all of these domains. That's one of the artifacts about these vector quantizing autoencoders. They really don't have very good out-of-domain generalization ability. So just doing that took over 2 weeks on 4 NVIDIA 840 GPUs.
Vista.
We use Vista for a lot of the follow-up work on this. And, so, I mean, it's all over the place.
Free Vista or?
He also has a follow-up paper, Voice Star, and we were doing experiments all over the place on this because but this is like the benchmark that we were using to basically say, you know, if you have A40 GPUs, then this is how long it would take. So transformer LM for the actual model itself, it's an 830 million parameter model with 16 layers, 12 attention heads with an internal dimension of 2048. And it basically takes a similar amount of time if you were to train on A40s. Another really cool thing is that actually during training, the in-painting masks, we choose them completely randomly. They actually don't need to be aligned with the word boundaries. So we don't have to do an inference of the start and end timestamps for each word as preparation for training. Okay. When we want to do inference, then given a waveform and a transcription of the original waveform as well as the one that you want to change it to, we actually do have to use an extra model to infer when the start and end times for each word are, so that we know which region of the waveform to cut out. And then after that, we do our rearrangement and give the sequence to the model to generate the in-painted section of the waveform.
Question.
Yes.
So people need to breathe, right? And usually they did it with words. So the problem is if you're changing, let's say, a short word with a long sentence, the places where people stop to breathe now need to change. So is that something you can handle, or will the kind of breathing stuff the wrong?
I think you'll see in some of the examples that the model is able to pretty convincingly, it's able to generate very, very realistic rhythms and with dramatic pauses and all kinds of stuff. Yeah, it's pretty cool. Okay, I'm going to skip this slide. So the evaluation, we manually crafted 310 editing examples because we wanted them to be very realistic. We didn't want to just randomly substitute words because we wanted people to we wanted to give the edits in the original speech to human raters and basically have them try and guess which one is edited or which one was more realistic. So we didn't want to be able to give that away just by choosing unrealistic word patterns. And so when we crafted that data set and then we generated all of those edited examples, we used Mechanical Turk to do side-by-side evaluations. And basically, if the takeaway here is that if you compare our edited speech versus original non-edited, unadulterated speech, and you ask human raters which waveform is more realistic, they would say that the speech generated by our model is equally or more naturalistic more than half the time to the original speech. There's also a big table of numbers here that I'm not going to spend too much time on, which just summarizes the voice cloning TTS results against all the state-of-the-arts at the time. And, we achieved the highest numbers on intelligibility, naturalness, and speaker similarity across the board. The field moves fast, and so there are new models now which are beating VoiceCraft. But at the time, we were the best, and like I mentioned, we kind of started the open source movement for these kinds of neural codec language models. After we open sourced ours, and everybody started doing the same. Okay, so now I want to talk about the demos. So speech continuation is what I'll start with. So essentially, we're just going to add words to the end of an utterance, and then synthesize the new speech at the end. So I'll play the original waveform.
What do I really want to do? I want to talk to the audience.
So that's the original, and then we're going to add, which is always the best part of my day, at the end.
What do I really want to do? I want to talk to the audience, which is always the best part of my day.
Here's one from Pulp Fiction.
The path of the righteous man is beset on all sides by the inequities of the selfish and the tyranny of evil men.
If you're familiar with the movie, you know, Samuel L. Jackson was reading a Bible verse, so we just looked at the next verse and just had him read that.
The path of the righteous man is beset on all sides by the inequities of the selfish and the tyranny of evil men. Yet he walks with unwavering resolve, guided by a compass of moral clarity and a heart unyielding in the face of adversity.
So, like I mentioned, it kind of learns, you know, through the statistics accumulated over a large amount of data, where to insert things like pauses for drama or for.
I think that's getting if there was a remainder, so if you added something in the middle of a sentence, then the pauses and the kind of.
Oh, at the
parts that are
end.
Not changing, do need to change, right?
I see what you're saying. Yeah, I guess if you added a really, really, really long, substitution in the middle, that might be the case. We haven't looked to see whether it would actually preempt whether it needs to insert a pause, to breathe in the middle there. It's an interesting point. And finally, one more.
I don't like to write down things that I don't mean.
This is Miley Cyrus, by the way.
I don't like to write down things that I don't mean. And when I was writing Wrecking Ball, I really poured my heart into it.
Can also look at editing. I'm just going to play a couple more examples before I move on. I want to highlight especially how it does a really, really good job at cloning the accent of the speaker. So I played this one already, which is Indian accented English. We can also look at a UK accent.
Fast cars, that had the nice clothes, that had the money, they was criminals.
We're going to add that had expensive gold watches into the middle of the utterance.
Fast cars, that had the nice clothes, that had expensive gold watches, that had the money, they was criminals.
And then here's one more, Pam from The Office. We're going to change amazing to beautiful, then add he just envies me at the end. So the model's capable of doing multiple edits simultaneously.
I saw it, and it was beautiful. Who said I didn't see it? Did Jim say that I didn't see it? He just envies me. I saw it.
Okay. So let's see, I think in the interest of time, I'm gonna skip ahead to the spatial sound understanding stuff, and then if we have a little bit of time at the end, I'll come back and I'll talk about the text control speech synthesis work. So now what I want to talk about is work done by my PhD student, Zhisheng Zhang, on spatial sound understanding, which was just published at ICML last year. So sound is a spatial phenomenon. A lot of the problems that people work on in the speech and audio community are done on monaural data. So just a single microphone channel with no spatial information. It's very easy to get that kind of data. And you don't always need binaural or multi-channel audio for tasks like speech recognition or speaker identification. But when we experience sound in the physical world, we're able to infer not just what's happening in terms of what people are saying or what sound events are going on around us, but also we can tell what the distance, the direction of arrival of each sound around us is. And this requires multi-channel audio to do. So there's a lot of very cool applications that we envision here for like search and rescue robotics, or really any kind of robots that need to infer where different sound sources are located in their environment. AR and VR, say glasses, especially for deaf users, that could tell you when there's a bicycle bell, approaching from behind you, or autonomous vehicles that might need to hear the siren of an ambulance, on the street over and infer which direction the ambulance is coming, to predict when they need to pull out of the way. So what we're going to be doing here is we're going to try to unify sound perception and reasoning in a spatial sense through a question answering task. So we built a new data set of 800,000 spatial sound question answer triplets. And we built a new data set because this was actually a new task that we proposed. Nobody had looked at this before. And we also proposed a new model that extends the Llama 2 LLM to process spatial audio input, which I'll talk about in detail. So I just want to say a couple quick words about human sound localization in case you're curious how we are able to localize sounds. There's a lot of different cues that your brain is able to use. So your head and your body create an acoustic shadow. Your head is mostly water, and so sounds, because of the mechanical impedance mismatch between the air and the water, tends to bounce off of your skull, and then it would echo around the room, and then it would hit your other ear. So because of that acoustic shadow, there's something called an interaural level distance. There's also an interaural time difference due to the fact that the sound takes a little bit longer to reach your left ear than your right ear if it's coming from your right. Either because it has to bounce around the room or there's a small amount of transmission that goes through your skull. And then your pinna actually has, so these things have an interesting asymmetric shape because they create little reflections sort of within them that slightly change the frequency response of your ear depending upon the elevation of the sound that's hitting it. So sounds coming from below versus above are going to sound slightly different because of the way they bounce inside your pinna. And there's actually something called a head-related transfer function that we can use to mathematically model these effects in binaural audio. So to produce data, waveform data, what we're going to be using is the Sound Spaces 2.0 simulator that was proposed by Kristen Garland's group here, along with her students and collaborators at Meta. So it's built upon the Matterport 3D simulator, where what they did is they added the capability to place down sound sources and receivers, and then basically did ray tracing sound propagation simulation within these environments. It's quite realistic. There's frequency dependent coefficients of reflection, absorption, and transmission attached to every single surface and material type. And what we're able to get out of it is a binaural audio, left ear and right ear, along with the head-related transfer function applied to them, with whatever the egocentric RGB view was for the receiver wherever they're located. In this work, we're actually not going to be using RGB. We're only going to be using the audio. I have a student who's currently doing some follow-up work where we are doing audio-visual perception, so we're adding this input back in. So when it comes to now creating the text data for the questions, we handcrafted templates to start based on 4 different categories. So detecting what sounds are present, detecting what their direction of arrival was, estimating how far away they were, and then doing spatial reasoning. So is the blank of the blank to the blank, is the sound of the blank to the blank of the sound of the blank, right? Where you could fill in, is the sound of the TV to the left of the sound of the parakeet or something like that. So given those question templates, what we're going to do is we'll run a giant loop where we will randomly select a scene, a room within, or sorry, an environment, a room within the environment. We will plop down a sound source or more than one sound source along with the receiver. We will randomly sample clips from a very, very large audio database of several million different recordings across 500 and some different sound classes. So this is the audio set data set. And then we'll play those through the sound source, and we'll record the sound as it was received by our simulated person. Then, given those ground truth parameters that we have access to, like the XYZ coordinates of all the sources and the receiver, we're going to use rules to essentially populate the blank fields of the questions. So if we know that we had the television class, and we are asking whether the television is behind you, we would then compare, the pose of the person to the location of the television and be able to infer that television is behind them. So the answer to this question should be yes. So we'll generate 800,000 of these kinds of questions, and then we'll paraphrase them with we use GPT 3.5 to do this in order to not have the language look too formulaic and templated. So I'll just play like one quick example of that. So this is the sound of the thunder further from you than the sound of the bell. Okay, so hopefully you could hear that the bell was sounding like it's closer to you than the thunder, in large part because it's louder, right? If you had headphones, you could actually listen to some of these other ones and you can hear the directionality of the different sound sources. Okay, so now I want to talk about how we add a special spatial sound encoder that can produce tokenized representations of these multi-channel audio recordings that can be processed by a pre-trained LLM. So what we're going to do is we're going to build, we propose this model, which we call the spatial audio spectrogram transformer. It's an extension of a well-known monaural audio spectrogram transformer that people often use for sound event classification, which only operates on single channel audio, so it doesn't have any ability to perceive spatial relationships. So what we do is we add this processing stack at the bottom here, which takes left and right audio channels, extracts log-mel energy spectrograms for the left and the right channel, and then phase spectrograms for the left and right channel. We compute the interaural phase difference and then map that to rectangular coordinates before stacking it all together and then doing a patch embedding. So we essentially have like left and right magnitude and timing information, as well as phase differences between frequency-dependent phase differences between the left and the right signals. We actually found that we had to pre-train this encoder on just standard sound event localization and detection tasks in order to get it to a good, initial parameter space before we could marry it to the language model and then fine tune the whole thing. So essentially what we do is we're going to have now a learnable projection from these tokens output by the spatial AST, and then we're going to do parameter efficient fine tuning on the llama model, where we give the model the left and right audios for the spatialized waveforms, along with the question, what is the sound on the left side of the sound of the dog barking? And the idea is that then the model would hopefully be able to predict, oh, I hear music, right? So we basically train it to predict the ground truth correct answer. Okay, so let's look at the results on spatial sound QA. So we break down their performance across the different question template types. So we have detection associated with predicting what sounds are present. Direction of arrival, is the TV coming from 45 degrees on your left side, or is it coming 180 degrees behind you? Things like that. Distance, how far away is the TV? Is it 1 meter, 5 meters, 10 meters? And then two types of reasoning: direction. So is the TV further to the left than the sound of the dog barking? And then distance reasoning. Is the person talking closer to you than the sound of the telephone? So those would be examples for each of those. So higher is better for all of these, except for distance, which is an error rate. These are all accuracies, and then we want distance error rate to be lower. So the random baseline is in the blue. It performs pretty badly on all of these different categories. We have a monaural version of our model, which performs significantly better than random on a lot of these, like detection, but on direction of arrival, it is essentially hopeless because it doesn't have any spatial information. And then our binaural model is doing much, much better on these task categories that require spatialized reasoning. So like distance reasoning, direction of arrival. And then finally, we establish an upper bound here with this oracle, where essentially what we do is we just take the ground truth system, or the ground truth like scene rendering parameters, all the XYZ coordinates of all the sources and their poses, class labels for the sounds that we were using, and we just linearize that and give it to the LLM and then fine tune it to answer the questions. And so you essentially get 100% accuracy and 0% error when you do that. So that's serving as our top line then, and you can see exactly where our gray binaural BAT model is. Okay, so I think we're at 1 o'clock. Should I end now, or?
You can take a couple more minutes if you want.
Okay, a couple more minutes. All right.
To you. I
I have 2 more things that I could show. Do people want to see video dubbing, or do they want to see like text-controlled synthesis, where you can type, an elderly woman with a rich Southern drawl speaks slowly, and we can synthesize audio? Which one do people want to see?
Second.
The second one. Okay. All right, so this is work which is done by Anush Taiwan, who's co-supervised by myself and Unsal. He's a PhD student here at UT, and this is work presented this year at EMNLP. So I presented our work on VoiceCraft, and we saw how joint speech text language models can perform voice cloning, text-to-speech synthesis via prompting. But in a lot of cases, content creators don't want to actually use an existing voice to do the generation of speech. They may instead want to describe in words the sound of the voice that they want. So you can imagine if somebody is creating like video game characters, or they want to preserve, they don't want to like violate privacy of by using somebody else's voice. Then they might want instead take this kind of approach. So where you might say like an elderly woman speaks eloquently in a smooth Southern drawl, rather than prompting the model with a waveform. So there are some data sets that are out there that have these kinds of style captions on a per recording basis, where you would have, maybe a speaker identity, a waveform, a transcription of the waveform, and then some, meta description of how that waveform sounded. So something could, one of those could be like in a slightly clean environment, a woman speaks at a slow speed with a medium pitch. So when we started looking at this problem, we kind of took stock of all the data sets that were already out there that had these kinds of style captions. And we really didn't see anything that we were happy with, because they were all either really, really, really tiny, only a couple hours of speech with a couple speakers, usually, 4 or 5 voice actors that were hired. Or if they were large scale, so thousands of hours of speech, then the captions were all super boring like this. They were all very, very basic things, just describing, how fast the speaking rate was, what was the pitch. But nothing that actually had like rich style descriptors like elderly or eloquently or smooth Southern drawl or things like that. So we set out to basically build a data set which would be very, very large scale, highly diverse, covering thousands of different speakers, but also covering very, very, very broad aspects of speech style. And then, of course, to make it open source. So we defined a new taxonomy of speaking styles, which is kind of like scale centric. So we said, okay, what are all the tags and ways of describing speech that we can think of that are easily extractable via signal processing tools? So we can get speaking rate, we can get pitch, maybe we can get gender classification with off-the-shelf classifiers. But then there's all these other things that are a lot harder to get. So what does it mean for somebody to have a shrill voice or a nasal voice or a silky voice or a husky voice? We can't just, we can't easily predict that by looking at something like a pitch tracker. We don't have DSP tools for extracting those. We don't have good labeled data sets for building models for those. The other axis that we then broke this down on was whether the tags were speaker specific, so something that could apply to somebody's voice across all of their utterances, or tags which were really situational, and we had to actually annotate on an utterance by utterance basis. So whether something was laughing or whispered or happy or angry and so on and so forth. So we wanted to avoid as much as possible doing any kind of manual annotation of these captions, because it's very, very expensive and time consuming to collect these kinds of annotations, especially if you want them to be very rich. So what we did is we developed 2 pipelines for automatically scaling the data collection, one pipeline for the intrinsic scaling, one pipeline for the situational scaling. So the intrinsic scaling is based upon collecting a seed data set of human annotations, where we take waveforms from famous actors from open source data sets, and we have people on Mechanical Turk attach descriptors to them. So Gilbert Gottfried would be described as having like a high-pitched grating voice, and Samuel L. Jackson might be described as having like a deep commanding voice or something like that. So we would take all of those descriptors that were human annotated, and then similar to how I described earlier in the talk, the speaker embedding model that I mentioned, we used that kind of model to then encode all of those waveforms into vectors that we could use to search for nearest neighbors over a very, very, very large speech data set. Specifically the Amelia data set, which has about 50,000 hours of English speech. So once we find those nearest neighbors, then we just said we're going to copy all of those annotations over to them. And this resulted in about 2,500 hours of automatically labeled data at this intrinsic level. And then scaling situational tags was a little bit different. We developed this 3-stage filtering pipeline where we started off with Amelia, and we wanted to look for highly expressive speech, because usually very, very neutral speech doesn't really have much in the way of situational descriptors that people can attach to it. So we used a model that predicts emotion features, specifically dominance, valence, and arousal features, and looked for utterances where those activations are very high. Then we took those utterances, looked at the transcripts, filtered them with Mistral to find those that matched the specific speaking style that we would use as a query. So for example, angry. And then finally, we used Gemini as a judge to retain the utterances where the audio actually matches that tag. So we would give Gemini the audio and say, does this audio match the angry tag? And after doing this 3-stage filtering, we got about 288 hours of automatically labeled data. So then you can look at the tag breakdown across the intrinsic and the situational data that we collected. About 2,800 hours in total. And it covers about 59 different tags. But of course, there's kind of this, long tail distribution where loud and enunciated are very, very common, but then things like scared or animated are relatively less frequent. So then what we did is we took a model, which this was an off-the-shelf model that was trained on one of those data sets that I mentioned earlier on the very basic tag taxonomies. It's called Parler TTS, very, very similar to our VoiceCraft model in that it's predicting these, diagonally delay patterns, neural codec representations of audio, and then using an RBQ decoder to map it back to a waveform. But it's adding this cross-attention branch where you can then give the model the style description, and in each layer it can attend to that. So this model, it's got about 880 million parameters, about the same as ours. And then this is trained for 840,000 steps on 4 H100 GPUs. So looking at the results here in terms of the human listening evaluation, this is style consistency. So how well does the generated speech match the style prompt on a 5-point Likert scale, and then speech quality, how natural is the speech, also on a 5-point Likert scale. Yellow is the ground truth audio. So this is like real data, which would match the style description which you use as a prompt for the model. And then the Parler TTS baseline only trained on the basic tags. It's substantially lower results than that. And then we bridge a decent amount of the gap between that baseline and the ground truth speech with our models. And even the base model using only that those few hundred hours of manually annotated data that we used as the seed is still doing pretty well, but we do see gains after scaling up with our automatic pipeline on both the quality and the style consistency. So now the fun part, let me play a few demos. So let's do a low-pitched guttural male voice speaks slowly in a clear environment.
You want to see how far you can push everything and as an artist.
A female speaker's voice is clear and expressed at a measured pace, but carries a high-pitched nasal tone recorded in a quiet environment.
Joe Bow, hockey mom from Wasilla, if I have an idea that would perhaps make...
I'll do one more. How about sleepy? A man speaks at a measured pace in a clear environment, his voice carrying a sleepy tone.
I mean, to be fair, I did see a UFO, so,
Okay, I'm about 8 minutes over, so I can go ahead and end there.
No, I'll stop here.
Okay,
Thanks.
thank you.
We could take one quick question. Go ahead.
So just down the line, maybe in the context of safety questions. So is the generalization quality so good that a forensic, let's say, voice identifier is able still to tell the generated output apart from the human?
So that's a very complex question because so remember, we're doing all the generation at the level of these neural codec representations. So you kind of have to separately establish whether that model is looking at artifacts that were introduced by the codec versus artifacts that were introduced by the LLM. So this is something that our lab is currently doing work on, and there's a lot of work within the speech community. There's every single conference, there's deepfake challenges now happening where people are trying to basically build detectors for whatever the latest generation of state-of-the-art models is. And also another focus now is trying to actually predict which model generated this particular deepfake, because there's so many models to choose from now that's sort of another thing that forensic analysts are interested in finding out.
Is there a methodic way to change the generated output in such a way that it's not detectable by human listeners, but by computer analysis?
So like watermarking or something like that. So that is another, that's another thing that a bunch of people have proposed watermarking techniques. The main thing that you run into there is that watermarks are not always robust to transformations, either like filtering you know, downsampling, upsampling, re-encoding versus decoding with some other audio codec. And so I think it's kind of an open research question. Can we actually produce watermarks which are robust to all of those different perturbations? There are some that work pretty well, but you know, 85–90% detection accuracy, is that good enough, right? That's the other question. So yes, people are working on that.
Just thanks, Dave.